Good day, everyone. I am Joseph of Digitalytic Solutions. I am a consultant, trainer, speaker, and a book author. Welcome to our course, Mastering Machine Learning Algorithm. In this lesson, we will learn about analyzing Gaussian Density Function. So you are expected to identify the concept of Gaussian Density Function, differentiate the shapes of Gaussian Density Function from each other, and appreciate the roles of Gaussian Density Function in machine learning. In our last lesson, we learned about Beta Density Function. We learned that this function can be used for continuous random variables that are restricted between 0 and 1. We said that this function is a function of two parameters. We also learned that Beta Density Function represents a family of probabilities, and this is a versatile way to represent the outcome for percentages or proportion. We discussed that we can think of A minus 1 as the number of successes and B as the number of failures. We highlighted the fact that it is most commonly used in machine learning in modeling the uncertainty about the probability of success of a given experiment. If you missed lesson number 9, the link is given in the description below. You may pause this video and come back if you're done with it. This makes lesson number 10 more meaningful. Because of so many events happening in this world, we have been looking for ways to model the general truth. The results are many, and Gaussian Density Function is one of them. Maybe you want to ask, what is Gaussian Density Function? What are its nature and properties? Of course, it's better to know all of them to make our understanding of this density function more meaningful and more significant. Before going to the challenging mathematical expression, it is always better to know how it is identified so we can properly appreciate the equation. It is used in many continuous applications. It is used in all sciences. It is very interesting, isn't it? The reason is the remarkable result, which is known as the central limit theorem. I'm sure you know what the central limit theorem is. If you haven't known what this one is, then I suggest you study what a central limit theorem is, because this will make your understanding of this lesson even more meaningful. So because of this phenomena behind the central limit theorem, a number of variables may show empirical distribution that is close to the normal distribution. It accurately models large number of phenomena in this world. What is even more interesting about it is the fact that by intuition, this mathematically represents the general truth. The question at this point is, why general truth? The answer is, it defines measurable quantities that, when the values are accumulated, they tend to be similar values, but with only very few outliers. So with that being said, this equation follows the central limit theorem. And as what I have said, this is the reason for the remarkable result. It is also called bell-shaped or normal distribution, as you can see in here. So let's just think that this is a normal distribution and the bell shape is perfect. I'm sorry for my drawing, but okay. So it is defined by this equation. So you have this equation that defines this distribution. So let's define some of the elements in this equation for better understanding. So in our study of machine learning algorithm, we have to always take note of the different formulas, not necessarily to memorize each of them because we can just actually Google them, but at least we have some knowledge on how they operate in our field, especially if you would like to master machine learning. So I guess, and I really suggest that, I strongly suggest that you really have to memorize, if not just familiarize these formulas. Okay, so U or mu here, this one, okay, is the median. And this one is the standard deviation. So of course, the mean and the standard deviation of the population of all possible observed values of the random variables that are considered. Of course, not just 90% of it, not just 70% of it, but we consider all the values of the population. And then we have here, okay, so we had that in our elementary math, and everybody knows that this is pi. Okay, this is pi, and the value is 3.14159 ... And this means the e here, sometimes you can see that this is like here. This is like this. Okay, and that means exponential, and it has a value of 2.71828. I think I need to write 2.71828. Is that seen? Okay. So now, after knowing some of these elements of the formula, I think it's better to know what are the properties of the Gaussian density functions. So let's have the properties one by one. There are actually 5 properties, and we're going to go through one by one so you would be able to understand it. Okay, so the first is that it is an entire family of normal probability distributions, and because this is so, its specific shape is determined by its mean and its standard deviation. So later we will have the different shapes. So whatever the shape is, then it is dictated by its mean and its standard deviation. What could be the shape when the mean is higher? What about the shape when the mean is lower? And what about when the standard deviation is lower vis-a-vis the mean, and also when the standard deviation is higher vis-a-vis the lower mean or higher mean? So we will have that one later. Then the second property of this distribution is the highest point, okay, on the normal curve can be found at the mean. The highest point at the mean, which can be also the median and the mode of the distribution. So that means we can find the mean, the mode, and the median at the center. Alright? Now, what about the third property? The next property is the normal distribution is symmetrical. What is the meaning of symmetrical? From the word symmetry, it means there's balance. So this means that the shape of the curve to the left, where is our left? This is the left, okay, is the mirror image of its image to the right of the mean. So this is to the right, and that means this is the mirror image of the image at the right side. So because it's an mirror image, that means they are identical, okay, because this reflects its image here at the left. So they have the same shape, the same face value, the same symmetry, of course. Now, what about the fourth property? The fourth property is with respect to tails. Okay, so now we are done with the upper one. What about the tails? What are the properties that can be found at the tails? So the tails of the normal the normal curve extend to infinity. So if you're going to extend this is unending extension of the tails. Okay, so it means unending in both directions, left to the right, but never touch the horizontal axis. So no matter how we extend the lines, both lines, left and right, they could not meet this axis. We call this the horizontal axis. They will never meet. Okay, they will never meet. So we call that asymptotic. But one thing you must remember is that the tails get too close to the horizontal axis to ensure that the total area under the normal curve is equal to 1. Remember our lesson before, we said that the area under the curve is 1. right? Next. Now let's go to the last property. The last property is, since the normal curve is symmetrical, the area under the normal curve to the right, where's our right? Okay, this is our right, of the mean is equal to the area under the normal curve to the left of the mean. Remember, they are symmetrical, and this one is the image of this part. So since the total area is 1, so each part has an area of 0.5. So 0.5 for the right, and we have 0.5 for the left, and so when we total that, that is equal to 1. Okay, 1, because the total area of the curve is always equal to 1. If that is above it or below it, then something is wrong. Now, let's examine some of the shapes for better understanding of this lesson. So this is what I've told you before, what would be the situation if the mean is lower and the standard deviation is higher. Now, there are 3 shapes here, and then we will have one by one. So let's have the first shape, letter A shape. So these are the 2 normal curves. Again, sorry for the drawing, let's just think that these are perfect normal distribution. So these are the 2 normal curves with different means, but of the same SD, or standard deviation. So if mu1, or the mean one, this is the mean one, is greater than the mean 2, the normal curve with mean 1 is centered farther to the right. But let's think that they have equal standard deviation, but the mu1 has higher mean, so it tends to move going to the right, and the lower one, which is in this case mean 2, is going to the left. So that is the situations. Okay, let's go to our situation number 2. So this is 1, and this is the 1. Now, as you could see, we have again 2, but what is different from letter A is like this. So this describes again 2 normal curves with the same mean but of different standard deviation. So unlike in our first situation, now in this case, what varies is the standard deviation. So we have standard deviation 1 and we have standard deviation 2. So as you can see, standard deviation 1 is greater than the standard deviation 2, but of course their mean is the same. So because of this, the normal curve with standard deviation is more spread, this one is more spread than the normal curve with standard deviation 2. Again, the standard deviation 1 is larger or higher than the standard deviation 2. So what does this imply? Okay, this scenario implies that the larger standard deviations, this implies that the larger standard deviations result to normal curves that are flatter and more spread out. So on the contrary, those with smaller standard deviation like this one, okay, have normal curves that have higher peaks, which is sometimes pointed and are less spread. So that is the situation if the argument has something to do with the higher and the lower standard deviations. So now let's have our last shape. So let's make the shapes more interesting this time. So in this case, let's consider a random variable x that is normally distributed. Again, of course, it's a normal distribution. So it's normally distributed with mean and standard deviation. So considering that a and b, okay, the probability of a, which is equal to or less than x, which is less than or equal to b, are numbers on the real line. So we can expect that x will have a value between a and b. Okay, so this equals the area under the normal curve with mean, mu, and standard deviation corresponding to the interval a and b. So what would be the case of x here? So this is the situation. Okay, so as you could see, we have here the area wherein x is present and our a is here and our b is here. So that is the part of the curve where x can be found. Since we are emphasizing that the normal curve, or about the normal curve, so we cannot help but mention the empirical rule. So this is actually very important when we talk about normal distribution or the normal curve, because this tells us more significant ideas about what to expect and the insights we can get out of the data that we have. Okay, so this picture shows that the empirical rule. So what is this all about? So this area, okay, of course this one is the mean. Okay, this is the mean. So let's have this one first. The first from this distance going to this distance. Okay, so these areas are the basis for the empirical rule for a normally distributed population. So let's have this value, which is 68.26. So what's the meaning of this? So 68.26% of all possible observed values of x are within plus, this is the plus, or minus 1 standard deviation of the mean. So from the mean, plus 1 standard deviation, going to the left, minus 1 standard deviation. So the value is 68.26. What about if we're going to add another standard deviation from to the left and to the right? So how much will it be? So it is 95.44%. So what's the meaning of this number? So 95.44% of all possible observed values of x are within plus or minus 2 standard deviations of the mean. So 1, 2 going to the right, 1, 2 going to the left. Now let's have the last one. So what's the value for the last one? So it is the 99.73. That's 99.73, which means that 99.73% of all possible values or observed values of x are within plus or minus 3 standard deviations. So we have 1, 2, 3 going to the right, 1, 2, 3 going to the left. Alright, so that's it. So recall that for continuous random variable, it is the cumulative distribution function, or CDF, we said that, and not the PDF that we use to find the probabilities. So the reason for this is the fact that we are always concerned with the probability of the random variable being in interval. Remember? So in our lesson for the continuous random variable, we always mention about A and B, remember? So with this said, we can reduce it to probabilities for standard normal distribution. So we can use standardization. So what is this? So the probability calculations for any normal distributions can be reduced to calculations for standard normal distribution. So we can use a common shorthand for the Gaussian Pdf. So this is the shorthand for the Gaussian Pdf. So this is the density function for the random variable x is normal with mean and variance. What is this for? Why do we have to study this? It is used to find nonlinear regression. It is also used to reduce dimensionality through identifying which dimensions of a dataset have a large variance. This may store very useful piece of information for your business, for your organization, for your agency. After all being said and done, let's try this. What is a Gaussian density function? How is the shape of the distribution affected by the mean and the variance? How is it related to machine learning? Comment your answer below. Do not forget to subscribe, like, and share. Please click the bell button to be notified every time we have a new session. Learn data science for free. See you in the next session.